It's gonna become limit of S times Y ref and divided by oh, sorry, this is Y ref of S, right? That's why I was wondering, like, why am I getting the wrong answer? Y ref of S, sorry. So if Y of t, let's say it's 1 U of t, Y ref of S, it's gonna be 1 over S, right? If you want to reach 1, it's S domain, it's going to be 1 over S. So I was wrong saying that this is not a variable of S. It is a variable of S. So this is going to be, let's say, Y ref over S. Okay? And this becomes S minus 1 divided by S minus 2. This would cancel out. So it would become S goes to 0, right? So this is going to be 0. So it would become Y ref divided by 1 over 2. So it becomes 2Y ref. Thanks God. Okay, so you see that, like, you can easily find the steady state error using the final value theorem. Don't make the mistake that I made first. Like, you just like have to remember that this is the S domain Y ref. If you have a constant in the time domain, let's say like K, in the S domain, it becomes K over S. That's why I did here. Okay, perfect. So this is the application of final value theorem in calculating a steady state error of a closed loop system. Okay, I can even like make this a little bit simpler. If you call this transfer function T of S, Y of S is equal to Y ref of S times T of S, right? And the error is Y ref of S minus Y of S. So it's Y ref of S minus Y ref of S times T of S. It's equal to, if I factor out Y ref of S times 1 minus T of S. Okay, so limit of E of t as t goes to infinity is equal to limit of S ES as S goes to 0. I can just replace this one here. It's going to be equal to limit of S times S times Y ref of S times 1 minus TS as S goes to 0, right? So this is another way of writing the same thing. Here it's where you have like the controller and the controller and the plant transfer function all together. You can use this formula. If you have the closed loop transfer function, you can use this formula. Let me write it down like a little bit more clear. So it's going to be limit of S times Y ref of S multiplied by 1 minus T of S as S goes to 0. Okay. So that's the application of final value theorem in calculating a steady state error. I hope that was clear. Now, okay, so far whatever we've seen, it's just control theory. It doesn't have anything to do with power electronics. This is general, it can apply to any system. Okay, now let's see some application in power electronics. So you guys saw buck converter in this course and also in ELEX 3130. Buck converter is basically a step-down converter. It would have a switch. It can be MOSFET or IGBT. It has a diode. It has an inductor, and it has a capacitor. And then we have a load here, right? So it would take a DC voltage and it would step it down to a lower output DC voltage. Okay, so what we did in this course, we saw that we calculate the duty cycle for this switch, right? It's a switch mode power supply. So we calculate the duty cycle for this switch to get the desired output voltage, right? So whatever we did before our first midterm, it was basically something like this. We calculated D. We would figure out if we are in the CCM mode or DCM mode, and based on that we calculate the proper D, and we would expect that the system would give us the desired output. Well, that's a little bit too ambitious to think that like everything is going to work perfectly fine. There are some simplifying assumptions that we made. There are noises in the system. None of these elements are ideal. So like a capacitor might have some resistor, definitely has some resistance. So does the inductor. The diode would have some voltage drop. There's some switching losses. So like there are many different things that we didn't take into consideration, right? So there's no guarantee that if you just like have an open loop system, if you set your D to the value that you calculated, you get the output that you desire, right? So we want to be able to have a feedback control. So we want to have a feedback control for this so that we can measure the output, and based on that, based on the difference between this output and the reference output, we just want to be able to adjust the duty cycle, right? So this is what we want to do. But the first thing that we have to do, we have to find the transfer function of this system. We have to find the GP of S. Okay, so that part, it's not that difficult to do. We did it in before the break, but let's do it one more time. So we want to model this as a system that takes an input and gives us an output. Okay, so first of all, we have to decide like what's our input. So like we already said that we want our D to be our input, the duty cycle of the switch, and we want our output to be the output voltage. Okay, any system would need some states, right? That like the differential functions that you write and the variables in the S domain, there are some parameters that you have to decide for our system what are the states. For an RLC circuit,